Hello. A warm welcome to all our dear participants. On the eve of National Science Day, today we have gathered here to unravel certain mysteries of the universe. Today, the topic of our webinar is the accelerating, expanding universe. And we have with us Dr. Bharat Ratra. This webinar is organized by Department of Physics, Surendranath College, under the DBT-Star College Strengthening Scheme. I'm happy to announce that today we had 445 registered participants, out of which we have 355 UG and PG students, faculty, almost 80 faculties have registered, 5 postdoc and PhD students, and 5 school students too. So we have, it's a kind of, on Science Day, we at Surendranath College thought that what a better way to celebrate this National Science Day than having a popular talk on the universe. So let's get on with the talk. And to start the program, I would request our principal, Sir Dr. Indranil Kaur, to please inaugurate the program. Over to you, sir, our principal, Dr. Indranil Kaur.
Am I audible?
Yes, sir.
Hello. Good evening, ladies and gentlemen. It's a wonderful that how the universe, where actually we are located at a very finer point, behaves and how it has actually come into being, or how actually things are getting changed during this 13+ billion years. And there are a lot of changes which are happening, and definitely lots will be known after today's webinar. And I understand that Professor Ratra will be really helpful in exciting your mind and making sure that the universe and the intricacies remain as an query for you for the next years to come. Thank you very much, and I wish the webinar a grand success.
Thank you, sir. In spite of your busy schedule, you could manage some time for us. Thank you so much. And now I would take the privilege to introduce our speaker to you. Bharat Ratra is a distinguished professor of physics at Kansas State University, works in the area of cosmology and astroparticle physics. Ratra joined Kansas State University in 1996 as an assistant professor of physics. He was a postdoctoral fellow at Princeton University, the California Institute of Technology, and Massachusetts Institute of Technology. Ratra earned a doctorate in physics from Stanford University. Ratra has received more than $8 million in individual and collaborative grants for his research. Ratra was a National Science Foundation Career Award winner in 1999. He was named a Fellow of American Physical Society in 2002 and a Fellow of American Association for Advancement of Science in 2005. He has received various other prestigious awards as well in his entire career. So now, without much ado, I would now hand over the mic to Dr. Ratra. Over to you, sir.
Thank you very much, Aditi. It's a great pleasure to be here. Thank you for inviting me, and thank everybody for coming. So I'm a cosmologist, and that means I study the structure of things in the universe and the structure of the universe itself, and also how they change in time. And it's a very, very exciting time to be working in cosmology because we've got very nice new telescopes both on the ground and in space with very sensitive detectors. The same kind of CCDs that you have on your phone, except they're more sensitive and they're bigger. And we've collected a lot of measurements that are relevant for cosmology. And in the last couple of decades, these measurements have reinforced two very, very striking results. I mean, the first one, I'm sure most of you are familiar with, is that when we look at what contributes to the energy budget of the universe at the present time, we find we don't understand what 95% of that stuff is. We understand the 5% that are atoms and molecules and the usual charged particles, but 95% of the stuff out there is not yet understood. And the other result that's probably going to prove to be even more profound if it holds up is that these cosmological observations are suggesting that either quantum mechanics or Einstein's theory of relativity are incomplete descriptions of reality, and perhaps both need to be improved upon. And that's a very exciting prospect. So I have this web page down here, which is designed by a group of friends, and it tells you how global warming works, and that's a really important thing now. And it would be useful if you're interested to go see that webpage and maybe publicize it. So let me move on to my rest of my talk. So I live in Kansas, and this is, it's in the center of the US. And this is a nature reserve outside of town, maybe about 10 or 15 minutes away by car. And these are bison, American bison. And this is a nice place to go hiking. So one can think about going on a hike. And if you think about that, you can kind of realize that there's some limits to how far you can go. And if you are very patient and you have a lot of time, maybe in your whole life, you could hike 100 kilometers or 1,000 kilometers. But beyond that, it's very, very difficult. It's really difficult to access 100,000 or 10,000 kilometers. And so there's some limitation. There's an upper limitation to how far you can go on length scales. And you can also think about the lower end too. So I think most people's fingers are sensitive enough to feel a single hair. And that's about maybe typically 100 micron or less than 100 micron. So maybe about 10 to the minus 4 meters. And so we kind of limited in the length scales we can directly access through our senses. And they're somewhere in this region. So I have a whole bunch of length scales here. The units are in meters. And a typical human is about 2 meters in length. And a typical hair is maybe 10 to the minus 4 meters. And 100 kilometers is 10 to the 5 meters. And you can access this region very, very easily with your senses. But when you get out to much higher, longer length scales or much shorter length scales, you cannot do the same thing. You have to use measuring devices like telescopes, or microscopes or particle accelerators, and you capture electronic signals from those. And you have to compare those signals or those measurements to your mathematical models for reality. So the way one builds intuition on these scales, which you can directly access, is very, very different than the way you build intuition on large scales and small scales. So on these scales we're very familiar with Newton's laws and Newtonian physics. I mean, it's kind of easy to understand how that developed. I mean, easy in some sense. I mean, it took a huge effort to get to that stage. But you can roll balls on surfaces and get some idea of friction, and you can collide balls together, and you can get ideas about conservation of energy and momentum, and you can drop things and get ideas about gravity. But you cannot do that on these scales. In these scales, you have to build mathematical models and compare those mathematical models to electronic signals you get from various measuring devices. So it's perhaps not unexpected that the intuition you develop here and you develop here is very different from the intuition you develop here. And on these scales, quantum mechanics is more important, and on these scales, relativity is more important. And the way to get good at this kind of physics is to try to develop some of your mathematical skills and your measurement skills. And it's often not appreciated how large a range of length scales these correspond to. So I want to spend a little bit of time walking through those length scales. So we're going to start out with a typical human scale, and I'm sure you recognize this person. And instead of measuring lengths in meters, I'm going to measure them in Einsteins. So an Einstein is roughly 2 meters. Instead of just doing length scales, I could have also done mass scales. Then an Einstein would be 60 kilograms, or I could have done time scales, and an Einstein in this picture would be roughly 50 years. But we don't have time to do that, so I'm going to just focus on length scales. I'm going to take a jump of a factor of about 10 million, and look at this picture of the Earth. Such a picture has only become possible in the last 60 or so years since we've had satellites out in space. Now, this is Madagascar, this is the Arabian Sea, and you can just see India over there. Can't see the Bay of Bengal because it's on the other side. But if you want to get some idea of this scale here, you can think of the diameter from the North Pole to the South Pole. And what you'd have to do is get 6.5 million Einsteins, put one on the other shoulder, and build a big, long tower of them. And it would be about 6.5 million Einsteins. So it's a factor of about 10 million to go from a typical human to the size of the Earth. And the Earth is a small planet. It's not that significant. We can go and look at the biggest object in our solar system, which is the sun. And this is a factor of about 100 in linear scale compared to the Earth. So if you had 100 Earths and you pile them one on top of the other from the North Pole to the South Pole of the sun, you would cover the diameter of the sun. So instead of 6.5 million Einsteins, you need roughly 700 million Einsteins to cover the Earth, the diameter of the sun. And the sun is just one typical star. It's a little bit bigger than average, maybe about twice as heavy as the average star. But we have larger scale distances to look at. And if you look at the Earth's orbit around the sun, it's roughly a circle. It's slightly elliptical, but it's not hugely elliptical. And you can kind of approximate it as a circle. And then you can think about the radius of the circular orbit around the sun. And that's 1.5 into 10 to the 11 meters. So another factor of 100 compared to the scale of the sun. So if you wanted to cover the distance from the sun to the Earth, you'd need to put 100 suns in a row. Or if you think about that in terms of the number of Earths you'd need to put in a row, it would be 10 to the 4. Or if you want to do that in terms of Einsteins, you'd need about 7 billion Einsteins, or 750 billion, 750 million. Well, I guess you can just divide that by 2 meters, whatever the number is. But the 10 to the 11 is kind of inconvenient to carry around when you're doing all your physics. You don't want to have to write down so many powers of 10. So astronomers who study the solar system tend to prefer to use different length units. And two conventional ones are the astronomical unit, which is the orbit, the radius of the circularized orbit of the Earth around the sun. And another option is to think about the time it takes for light to travel. Light is very interesting because in a vacuum, it travels at exactly the same speed, and it travels in a straight line, and no matter what it's doing, it's going to travel at the same speed. So that's, I mean, if you want to compare that to kind of human things, for about in a distance of a foot, light travels that in a billionth of a second. So light is extremely fast, and its speed is roughly 3 times 10 to the 8 meters per second. So if you divide this distance by this speed, you get a time, and that's the time it takes light to travel that distance, and it's 500 seconds. So when you're looking at the sun, and you shouldn't look at the sun with unexposed eyes. I mean, you need to have some protection, because if you look at the sun with your eyes, you're going to damage your retina and eventually go blind. And so you shouldn't do that. But when you look at the sun, you're not looking at the sun as it is at the present time. You're looking at the sun as it was 500 seconds ago in the past, because it took light that came from the surface of the sun 500 seconds to come to your eye lens and then hit your retina, and then those photons got converted to electronic signals that your brain processed and turned into an image. And so you're looking at the sun in the past and not at exactly the same time as you are right now. So we can step out and go another factor of 10 to the 5 or so, and that's to go to our nearest neighboring star to the sun, which is Proxima Centauri. And this has been in the news for the last few years. I think most recently they found, I think, a third planet around it, or they think they found a third exoplanet around it. And Proxima Centauri is about 10 to the 5 times further than the sun is from the Earth. And in terms of meters, it's roughly 4 times 10 to the 16 meters. Excuse me. In terms of light travel time, it takes about 4 years for that light to come to us from Proxima Centauri. Or in terms of astronomical units, it's about 200,000 astronomical units. And so we're starting to get back many, many powers of 10, even though we scaled everything to the astronomical unit. And that's getting to be inconvenient again. And so people who study collections of stars prefer not to use the astronomical unit or the meter for the length scale. They use something called the parsec, that's P-A-R-S-E-C, and the abbreviation is PC. And this is not that simple a unit to appreciate. So the way it's defined is shown in this cartoon here. So we take the Earth-Sun distance, which is 1 AU, and we take our observer and we ask her to go very, 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 very far away. So far away that this 1 AU subtends 1 arc second at her. And an arc second is a really tiny angle. If you go around a whole circle, you have 360 degrees. And you can divide a degree into 60 arc minutes, and you can divide an arc minute into 60 arc seconds. So it's a tiny angle. So obviously, because this is a huge distance, you have to go very, very, very far away for this huge distance to subtend a tiny angle. And when it subtends 1 AU with an angle of 1 arc second, this distance is said to be a parsec. And this is kind of a historical unit. It came out of astronomy, and physicists probably wouldn't want to use this unit if they kind of developed astronomy from scratch right now. They'd probably want to use light travel time. And in terms of conversion from parsec to light years, or the time, the distance light would travel in a year, it's 3¼ light years roughly. So 1 parsec is 3¼ light years. To get some scales, we can consider things like the furthest we sent humans, and that's to the moon. And the moon is about 1 1/3 light second away, or 1 1/3 second away. So when you're looking at the moon, you're not seeing it the way it is right now. You're seeing it the way it was 1 1/3 second in the past. We can roughly use the orbit of Pluto to give some idea of the scale of the solar system. And the radius of that is roughly 40 AUs, or in terms of light travel time, it takes 6 hours from light emitted by or reflected by Pluto from the sun to come back to the Earth. And the furthest humans have sent anything are the 2 Voyager missions launched by NASA. They were launched in 1977, and the numbers I have here are from the 40th anniversary, which is 2017. And Voyager 1 has gone 3 or 3.5 times the distance from the Earth to Pluto. So it's about 140 AUs. And in terms of light travel time, it's about 19 or 20 hours away from us. And that's the furthest we sent anything. So you can compare this to the distance between the sun and the nearest star, which is much, much further away. I mean, in terms of parsecs, it's about 1,000th of a parsec now. And this is roughly a parsec from us. So it's 1,000th of the distance to the nearest star. And it's done that in 40 years. So even the distance to a star is pretty huge. We can go out and look at even larger things. And this is a picture of our Milky Way Galaxy. And it's really good for you to try to see this. If you can get out of cities, you should be able to see it at certain times of the year. It's a big, bright band. And if you haven't done this, you should go try to do it and maybe talk to amateur astronomers and look at it. This is a really nice picture. We live inside this galaxy. It's a collection of maybe about 150 or 200 billion stars. And each star is typically roughly the size of the sun. The sun is maybe twice as heavy as your typical star. And this picture is put together. So we're living inside of this and we're looking outwards. And so this is a picture from inside looking out, and it's taken in little small photographs, and this has been stitched together and made into this huge, beautiful panoramic picture. This was done by the European Southern Observatory, or the ESO, and it's called, I mean, you can search for this on Google or some other search engine, look for ESO Galaxy or ESO Milky Way. And it's much better if you can look at it on your own screen and you can blow it up and look at various things. So it's a collection. Okay, maybe I should just move on a little bit and show you a few other pictures first. This is an old version of it, done with developing photographs at the Palomar Observatory in Southern California. And maybe the easiest one to describe and talk about is this artist's impression of the Milky Way. So the scale here from end to end, this is like a disc, like a frisbee, if you're looking at it from the top. And it's pretty large. So it's about, its diameter is roughly 50 kiloparsecs. A kiloparsec is 1,000 parsecs. So this is 50,000 parsecs. And if you want to turn this into light travel time, you multiply by 3.25. So it's roughly 160,000 years. So if you could travel at the speed of light and you started here and try to cross this, it would take you 160,000 years. And I mean, we can't travel at the speed of light because we have mass, but I mean, that just gives you some idea of the scale. So it takes 500 seconds from the Earth to the sun. It takes 4 years from Proxima Centauri to us. And it takes roughly 160,000 years to cross this. So this is a collection of stars, roughly maybe 150 billion or 200 billion. And there are other things, there's dust and there's gas. And these are all held together by their mutual gravity. And so you can kind of automatically deduce a few things from this, because we can see galaxies like this all over the sky. So it kind of suggests that galaxies are long-lasting phenomena and they're not short-lived. And so if they're long-lasting and gravity is acting, then you know what gravity is going to do. Gravity is going to pull everything in. And so the fact that you have this really large disk here immediately tells you that there's something that's preventing gravity from pulling those stars down to the center. And what's happening is there's systematic rotation. So the disk, and there's just kind of all the stars in the disk rotate systematically. They have kinetic energy, they have angular momentum, and because of the conservation of angular momentum, they're not going to all collapse down to the center of the Milky Way. And in the central bulge, the stars are not systematically rotating, but they're moving around randomly, and they also have velocities and they have kinetic energy. And so they're also not going to completely collapse down to the central part of the galaxy. And at the center is our black hole. It's not a huge black hole on the scale of typical black holes in galaxies. I think its mass is maybe 4 million times the mass of the sun. And a lot of galaxies have black holes that are a billion times as heavy as the sun. So we have a black hole, we have a rotating disk, excuse me. Now let me just, sorry. So we have a black hole, a rotating disk, and a bulge. And you can also see this black stuff over here. And this black stuff over here is not the absence of stars. There are as many stars in the black band as there are in the white regions above and below it. This is dust, almost like the dust you find around your house. It's little particles and silicates and other things. And this dust absorbs light and it blocks the starlight, so you can't see them in the visible. This galaxy is embedded in what's called a halo that's maybe 10 times the linear scale of the galaxy. So instead of 50 kiloparsecs, you're talking about 500 kiloparsecs diameter halo. And this halo is mostly just dark. There are a few objects in it, like we know of a couple of hundred of them. They're called globular clusters, and these are collections of 100,000 to maybe 1 million stars, and they orbit the center of our galaxy. The halo is where there's a lot of dark matter relative to the shiny stuff that we're seeing in stars. So this is our Milky Way Galaxy. There's many, many, many galaxies in the universe. This is our nearest neighbor galaxy. It's Andromeda, and if you haven't seen Andromeda, you should try to make an attempt to see this. You can see it with your naked eye at certain times of the year. It's a little bit bigger than the Milky Way, so it's maybe about 160 kiloparsecs in diameter, so maybe about 200,000 years for light to cross it. And you can see the central bulge, and you can see the dust lanes in Andromeda. It's a spiral galaxy, just like the Milky Way. So these two guys here are dwarf galaxies. They are orbiting Andromeda in the same way that planets orbit the sun. And they have hundreds of millions or even billion stars. The Earth has quite a few dwarf galaxies, maybe. Okay, can you hear me now? Okay, I'll just continue. If there's a problem, just let me know. So we have a lot of dwarf galaxies too, maybe about 40, but we cannot see any of those with the naked eye in the northern hemisphere. If you go to the southern hemisphere, you can see the large and small Magellanic Clouds. So Andromeda is about 750 kiloparsecs away from us, so roughly 15 times the diameter of the Milky Way. In terms of light travel time, it's about 2.5 million years. So when you look at Andromeda, the light that's hitting your eye that came from a star or some hot gas in Andromeda left that star or that hot gas about 2.5 million years ago, and it traveled in a straight line until it hit the lens of your eye and then hit your retina. So we're seeing Andromeda, when we look at it the way it was 2.5 million years ago. So we can go out to even larger scales, and some galaxies, if they're close together, start pulling on each other, and they form collections. And these collections are called clusters of galaxies. This one is relatively nearby it's so you're seeing the central region, and it's roughly maybe a couple of megaparsecs across. So megaparsec is 1,000,000 parsecs. And in terms of light travel time, you'd multiply that by 3¼ to get it in years. So that's maybe 5 to 7 million years to cross this. So every single spot of light you see here is a galaxy, and they're all typically containing maybe 100 billion or 200 billion stars. And each of those stars is typically the size of the sun. So this is a huge, huge collection of stars. And it's some significant distance from us. And you can go out even further and look at a patch of the sky. So this is, if you go back to the Milky Way over here, because of the dust and the fact that the sun is in the disk of the Milky Way, it's about, I didn't say this, about 1/3 of the way out. If you want to see the extragalactic sky, it's easier looking up over here and pointing your telescope up. And this picture that we're looking at here is pointing towards the North Galactic Pole. So in terms of the coordinate system we're using over here, it's spherical polar coordinates, and this is the polar axis, and the North Galactic Pole is here, and the South Galactic Pole is here. So we're looking at the North Galactic Pole, and this picture was taken, was put together by Shane and Vartanen at a telescope in the San Francisco Bay Area. It's in the hills outside of San Jose at the Lick Observatory. And by hand, they figured out the position of 400,000 galaxies and this map was made by Seldon Sibus, Peebles and Groth at Princeton. And what we're looking at here is a pretty large chunk of space. The scale here is maybe 300 megaparsecs. So in terms of light travel time, you multiply 300 million by 3¼ so it's about 1 billion years. So if you could travel at the speed of light, it would take you about 1 billion years to cross this. So this is a pretty large chunk of the universe. And you can see 3 distinct types of structures here. You can see the bright clusters, like that previous picture I showed you. This one is the Coma cluster, and it's about 120 megaparsecs away from us. The North Galactic Pole is very, very close to Coma. You can see other rich clusters. You can also see regions that are much, much darker. And these regions are dark, not because there's dust there that's absorbing the light, but they're dark because there are not many bright galaxies there. And they're called the voids. So we have clusters and we have voids. And we can also, if you look at this carefully, you can kind of see one-dimensional structures. And these are called the filaments. And this is where more of the brighter galaxies are. And if you look at this more carefully, you can kind of see the filaments come together. And where a number of filaments come together, you get the brighter clusters of galaxies. So one way to think about this is to think about soap bubbles in your sink or your bathtub. The interior of the bubbles are like the voids, and the brighter galaxies seem to not be there. The brighter galaxies seem to prefer to live on the bubble walls. And where you get 2 bubbles coming together, you get a one-dimensional structure where the 2 bubbles intersect. And those are the filaments. So the interiors of the bubbles are the voids, and the filaments are where bubbles intersect. And where a number of filaments run together, you get the clusters. So this picture shows us a lot of things. And one thing you can see is that when you look in different directions, you see very, very different structures. You could look over here and you'd see the Coma cluster with maybe 5, 6, 7,000 galaxies, each of them with a few 100 billion stars. Or you could look over here and you can see hardly any bright galaxies. So a distribution like this is called anisotropic. And that's kind of a little bit of jargon. So if you, at one point, and you look around you in all directions, if you look to your right, and you look to your left, and you look above you and below you and in front of you and behind you, if you see exactly the same thing, you are in an isotropic distribution. But if you do that right now where you are, you'll see different things in those directions. And the same thing's true if you kind of just think of yourself maybe a kilometer or 2 kilometers off the surface of the earth above Calcutta, and you look down at it, you're going to see different buildings in different directions. You're going to see the Bay of Bengal in one direction. You can see the Himalayas in another direction. And the surface of the earth is very, very anisotropic. And if you think about the solar system, it's also very anisotropic. In one direction, you see a big star, which we call the sun. In any other direction, you don't see that. And even on this scale of hundreds of millions of light years, it's very anisotropic. You look in different directions, you see different things. The really strange thing that happens is when you go a factor of 10 or so more and look at a larger scale, this completely changes. So what we're looking at here is a picture of the Blackbody radiation that was left over from the Big Bang. This was taken by the Planck satellite, which was launched by the European Space Agency. And this radiation is in the microwave part of the spectrum. So some of you have probably used microwave ovens to cook with, and that's kind of the same kind of radiation. It's a millimeter, a fraction of a millimeter wavelength radiation. And so this Planck satellite was sent up, and it had microwave detectors on it, and it looked at things from all directions around it. And it collected this microwave light and measured the frequency and the temperature. And so the way you want to think about this is you're inside a big ball, maybe a huge football, and you're looking in all directions around you. And the way I'm showing you this on this two-dimensional surface is I slice that ball from the North Pole to the South Pole, and I've opened it out. And so if you want to put this back together, you should take this edge and stitch it together with this edge and think of yourself as being inside of this ball. You do something very similar when you're thinking about putting the surface of the earth from a globe onto a flat plane. So we're looking out in all directions here, and we're measuring different temperatures, and there's some hot spots and some cold spots. And the first thing you might want to do is get the average temperature, and the average temperature is about 3 degrees Kelvin or 2.75 degrees Kelvin when you average it over the whole surface. And when you do that, and do that average, it's a really tiny number. So the room you're sitting in right now is roughly 300 Kelvin. So this is very, very cold. The thing that's more interesting is that when you compare the temperature differences between the cold spots and the hot spots, the temperature difference is about 30 microkelvin, so 30 millionth of a Kelvin. And compared to the average, which is 3 Kelvin, so 30 microkelvin divided by 3 Kelvin is 10 to the minus 5. So it looks roughly the same whether you look here or you look here or you look here or you look here. The difference is 1 part in 10 to the 5 or 0.001%. So this picture, the largest scale picture we can currently make of the universe, it shows you that it's isotropic to 1 part in 10 to the 5. And these are two very, very, very important facts about the universe. One, that locally around us, and this means on scales even up to tens of megaparsecs or so, that the distribution of both matter and electromagnetic radiation is bumpy. It's different in different parts of space, in different directions. It's spatially anisotropic. But when you get out to hundreds of megaparsecs, then the distribution, when you average it, of both the matter and the electromagnetic radiation is isotropic in space. And I'm not going to spend any time discussing these further in any detail. We'll make use of them a little bit, but if you want to understand where these might have come from, you can study the inflation model of the early universe, and that's thought to be the best explanation of both these facts. And inflation has not yet been completely established, but it's kind of the leading model for what happens before what people used to call the Big Bang. And you have to be a little bit careful when you go search for things on the web. You should only look at reputable sources. Wikipedia is pretty good, and Scientific American and Physics Today and Discover and Astronomy and things like that, if you can access them without having to pay. Okay, so we want to move on to something that's even more stranger, another fact about the universe. So if you look at this on very large scales, people say the universe expands, and that's something that's not that easy to appreciate. So if we are going to say that something is expanding, that automatically implies that we have measuring devices that are not also expanding the same way. And so sometimes it's kind of helpful to understand why the measuring devices are not expanding. So when we're talking about measuring devices, maybe we can think about a meter stick and to kind of understand what's happening there. So on the scales of meter sticks and larger, only two of the forces are relevant. So one force is the electromagnetic force, and the other force is the gravitational force. And you're quite familiar with the gravitational force. If you drop something and you don't support it, it's going to be attracted towards the Earth, and the Earth is going to be pulled towards the thing that's falling towards it. So gravity is always attractive if you have ordinary matter. Electromagnetism is a little bit more complex. So there's two kinds of charges. There are negative charges, for example, electrons, and there are positive charges, for example, protons. So if you bring two like charges together, whether they're electrons or they're protons, electromagnetism is going to repel them. But if you bring a proton and electron closer together, they're going to be attracted. So both these forces, the Coulomb force for electromagnetism and Newton's force, Newton's law for gravity, they're both inverse square law forces. So if you double the distance between the two objects, whether it's the two masses or the two charges, the force goes down by a factor of 4. If you triple the distance, the force goes down by a factor of 9. So they're both inverse square law forces. So we can kind of think about maybe two protons relatively close together. They're going to be pushed apart by electromagnetism, and they're going to be pulled together by gravity. And so it might be useful, if you haven't already done this exercise, to compute the ratio of the electromagnetic repulsion to the gravitational attraction. And this is going to be independent of the distance between those two charges, because both those forces are inverse square law forces, and the r squared cancels out. And so if you do this, you'll find that electromagnetism is 36 powers of 10 stronger than gravity. And so electromagnetism is a really, really dominant force. And that's kind of an important thing to realize. But when you get to larger scales, you don't have free charges around there. So if you kind of think about yourself and your friend in class, when you're sitting next to each other, you're not pulling or pushing your friend away electromagnetically, because both of you are neutral, roughly, because you're made up of atoms and molecules. And if you just focus on an atom, there's a positive nucleus, and then you have the negative electron cloud around it. And so the atom is electrically neutral. So if you have atoms in you and in your friend, the electrons in your atom are going to repel the electrons in her atom, and the protons in her atom are going to repel the proton in your atom. But the electrons in your atom are going to attract the protons in her atoms, and so on. And so the repulsion and the attraction cancel out. But you are pulling on your friend gravitationally, and it's an extremely weak force. But if you think about two nearby stars, they're much, much more massive. And so Newton's inverse square law has an m1 times m2 in the numerator, and the m1 and the m2 are much bigger for stars. So gravity is much bigger force between two stars than it is between two humans. And stars are roughly neutral also. So as you get to larger and larger scales, you can go from stars to galaxies, and gravity is going to be even more significant there, and electromagnetism is going to be even less significant. So in very, very large scales, gravity dominates, even though it's much, much weaker than electromagnetism. And this happens because basically everything's made up of atoms and molecules. I mean, there's a few charged particles around, but not a huge amount. And so on small scales, like on the scale of your meter stick, electromagnetism is the dominant force, and it holds it together, and gravity does not affect it that much. And this is a really interesting thing if you think about it really carefully. You're made up of atoms, and your nucleus in those atoms is a factor of 10 to the 4 smaller than the electron cloud. And there's pretty much nothing between the nucleus and the electron cloud. So you're mostly made up of empty space. And the chair you're made up of is also made up of empty space. And the wall around you is also made up of empty space. So the fact that you cannot fall through the chair, even though you're empty space sitting on empty space, or you cannot walk through walls, even though the wall's mostly empty space and you're empty space also, is because you're made up of atoms and you have these electron clouds. And the electrons, if you just kind of think of a meter stick, you have atoms and they're atoms right next to each other. And the electron clouds are pushing each other apart, but they can't go anywhere because they have other electron clouds on the other side of them that are pushing them also apart. And so that's why you have rigidity. And so even though you're completely pretty much empty space, you're extremely rigid because the electrons don't like each other. So that's what holds the meter stick together. And when you get to really, really large scales, gravity dominates. And on these very, very large scales, we have to use our best model of gravity, which is Einstein's theory of general relativity. So Newton kind of had this idea that we could have a fixed space and a uniform time, and physics would happen in this fixed space and time would run uniformly outside of it. And physics just happened in this uniform time that Newton had conceived of. And then early in the 1900s, Einstein came along and he realized that he could make a more accurate description of reality if he could make space and time dynamical and participate in physics. So instead of just having balls collide in a fixed space with a uniform time, he said physics is better described by allowing space and time to be dynamical. And he started out with the special theory of relativity and eventually generalized that to including accelerations, and that became the general theory of relativity. So special is special because you only focus on non-accelerating inertial frames. And the general theory of relativity describes acceleration, and because gravity causes acceleration, it also basically ends up describing gravity. So what general relativity does is it kind of wanders around in the universe and it looks for regions where there's slightly less mass. And what it does in that region is that it creates space. And so we can do a couple of little toy things here. So I have a kind of cartoon demonstration up here, and I'm going to try to show this to you. So this is a rubber band, and it's got, I don't know if you can see, I guess you can see this, it's got a wave drawn on it. So you can see your wavelengths here, and you can bring your centimeter or meter stick here, which is held together by gravity, by electromagnetism, and you can measure the wavelength. And if I have an expanding universe, you can watch what happens. As the universe expands, the wavelength gets bigger. And if the universe contracts, the wavelength gets smaller. So if I start out with shorter wavelength blue light and the universe expands, as time goes on, it becomes purple, and then it could become red and infrared. And so that's what expansion does, because this light has to live in the space. This demonstration is a little bit misleading for a couple of reasons. So firstly, this expansion does not happen in just one dimension. It happens in all dimensions. We live in a three-dimensional space. So you need, you can draw a Cartesian coordinate system in your room, and you need to specify 3 points relative to your origin to specify where you are. So we live in a three-dimensional space, and we have expansion in all dimensions. And this expansion of general relativity is not caused by gravity going to the edges of the universe and pulling. It's caused by gravity going into space and creating new space and pushing things apart. So I have a bit of a cartoon picture here also. So we have this rubber band here, and we have a meter stick that does not expand with the expanding rubber band, so we can measure the wavelength. And this is it at an earlier time. And as time goes on, it gets bigger and bigger, and we get a longer wavelength. And we need some way of describing the size of the universe. And a very naive way to think about it is to think about this distance between the hands as the size of the universe. And as time goes on, this distance gets bigger and bigger. So physicists take a local version of this, which they call the scale factor. And the symbol of that, symbol for that is A, and it's a function of time. And time runs this way. As time gets larger and larger, the universe gets larger and larger. And it's pretty easy. You can draw this and see that the wavelength is going to increase proportionally to the size of the universe. Astronomers don't like talking about scale factors, so they prefer what they call the redshift. And this is defined this way: 1 plus the redshift z is equal to the size of the universe now, so this distance, divided by the size of the universe when that light was emitted. So suppose you have a quasar here that emitted a pulse of light, and as time went along, it got larger and larger, the wavelength got larger and larger. So in the past, the scale factor was smaller than it is now. So this is a number bigger than 1. And so the redshift would be bigger than 0 as you go back into the past. If you come to the present time, if you take this to be the present time to be now, then this is unity and the redshift is 0. So the redshift is a variable that increases as you go back in time, and time is a variable that increases as you move forward in time. So this is the cartoon description of the expansion of the universe. And the guy who first realized that the universe was, he didn't realize the universe was expanding, but he found this redshifting. So this is Slipher, and he found this in 1912, and this is the telescope he used. So he looked at external galaxies, and he captured that light, and he passed it through diffraction gratings and broke it up into its spectrum. And he found that the spectrum, he could identify the ratio of wavelengths he was seeing, and he could relate them to the same ratio of atoms and molecules that he was familiar with. But when he started measuring the wavelengths he was seeing and comparing them to the measurements of wavelengths he could produce by heating up these atoms and molecules in his lab, he found that the wavelengths he was getting through this telescope were longer than the wavelengths he was finding in the lab. So if you kind of think of this in terms of the Doppler effect, if you've listened to a police car or an ambulance or a fire engine with its siren on, as it comes towards you, the pitch or the frequency goes up, and so the wavelength is getting smaller, and as it recedes from you, the pitch or the frequency goes down and the wavelength gets larger. So you get a blue shifting when it's approaching you. It comes, if it was redder, it turns more blue as it approaches you because it's coming towards you. And you get red shifting as it moves away from you. That if it was emitting blue light or blue sound and it moved away, it would appear redder. So the Doppler effect is also true for light, not just for sound, but it becomes a little bit trickier because for light, you have to account for relativistic effects, and one of them is time dilation. So the formula for the Doppler effect for light is a little bit different than the Doppler effect for sound. But so Cypher found this redshifting, and he didn't really know what to make of it. So you can kind of think of this, you have these guys moving away from you. And so one obvious option is that there was a big explosion in the past and everything was moving away, and it's like a firecracker, but that's not what's going on. So let's back off a little bit and think a little bit about galaxies and the expansion of the universe. So galaxies are pretty well described, and I guess you can't really see all these ping pong balls because there's a whole bunch of them, but maybe you can think about this experiment. So I have ping pong balls here on a rubber band, and I guess you can sort of see the black rubber band, but the ping pong balls are like the galaxies. The expansion of the universe does not affect galaxies now. When galaxies were forming and they were much more diffuse, things were a little bit different, but for mature galaxies, they're not significantly affected by the expansion of the universe. So what's happening is that the space between the galaxies is being increased, and the balls remain the same size, but the distance between them gets larger and larger. And here's a bit of a cartoon description of what's going on. We have some bread with chocolate chips in it. And I'm trying to describe a flat universe, a three-dimensional flat one. So you can see the 3 dimensions over here. We have a vertical dimension and 2 horizontal dimensions. And so if you kind of think about this for a second and you can walk through the bread and look at the edge, if you look outside, it's going to look different than when you look inside. And so this cannot be even a toy model of our universe. So it's actually just a little cutout piece of it, and it's going to go out to infinity in all 3 dimensions, because if it didn't go out to infinity, you could go to the edge and you could look out and the outside would look different than the inside. And I argued that it's isotropic and it should look the same in all directions. And the way you make this isotropic is you take it out to infinity in all 3 dimensions. So if we think of these chocolate chips as our galaxies, and we let the expansion go, then we can ask what an observer sees if she's on number 2. And what she's going to tell you she sees is she's going to tell you every galaxy is moving away from her. And you ask an observer on number 4 what he sees, and he's going to tell you every galaxy is moving away from him. So the fact that Slifer saw all these galaxies moving away from him doesn't mean he's at the center of the universe and that there was a big explosion at some time in the past and he's just seeing the debris of that explosion. This is actually the more correct description. Every point in space is moving away from every other point in space, and we live in a 3-dimensional space, so that's a little bit difficult to visualize. So the Big Bang was not an explosion at one point in space at some time in the past. It was sometime in the past, every point in space started moving away from every other point in space. And some years after Slifer, Hubble came along, and this was in 1929. And he had a better telescope than Slipher's. So he had this 100-inch telescope at the now called the Hale Observatories, which is in the mountains outside of Los Angeles in Southern California. Excuse me. And he could collect much more light. And with this bigger telescope, he could resolve individual stars in these galaxies Slipher had looked at. And he found some stars that he saw were pulsating, and he realized these were Cepheid variable stars. And these were extremely useful stars to be able to identify. And that's because of a discovery Henrietta Leavitt had made early in the 1900s. So Henrietta Leavitt was what was known as a computer then. She worked at the Harvard-Smithsonian Center for Astrophysics in Cambridge in Massachusetts. And this was where they collected all these photographic plates that observers took from telescopes all over the world. And astronomers, especially some observers, they're pretty obsessive, and they like taking pictures of the same region of the sky over and over again. And that's a really useful thing to do, because then you can identify transient phenomena. So Henrietta Leavitt had these plates of the same region of the sky taken at many, many, many different times. And she realized that some of these stars that she was seeing, that they were pulsating, they would get brighter and dimmer and brighter and dimmer. And she tried to find some of these nearby stars to which she could measure distances. And once you know a distance to a star, you can use a photometer and you can measure the wattage of the star. You can measure its absolute luminosity. And so she knew the absolute luminosity of some of these pulsating stars. And she was able to correlate the absolute luminosity with the pulsation period. So stars of certain pulsation period had certain absolute luminosities. So even if you couldn't measure the distance to a Cepheid variable star, if you could measure its pulsation period, you could measure its wattage. And so Hubble used that relation, this Leavitt period luminosity relation, to measure the wattage of these stars. And then he used the inverse square law for intensity of light to measure the distance to the stars. And he realized that there was a very simple relation between the speed at which these galaxies were moving away that Slipher had measured using the Doppler formula, to the distance these galaxies were at that Hubble had measured, Hubble and Humason had measured using the Cepheid period luminosity relation Henrietta Leavitt had discovered. And so a galaxy twice as far away was moving twice as fast. A galaxy 3 times as far away was moving 3 times as fast. And I'll just show you this, which is the Hubble law, and I'll probably just stop here because I think I'm starting to run out of time. So we'll focus on the upper panel. This is the recession velocity of the galaxy, and this is the distance the galaxy is from us. The distances are down here. So a galaxy 100 megaparsec away is moving away at roughly 7,000 kilometers a second. A galaxy 200 megaparsecs away is moving away roughly at 14,000 kilometers a second. And the slope of this is the Hubble constant, h naught. And that's roughly, in very strange units, it's 68 kilometers per second per megaparsec. And the units are strange because astronomers measure velocities in kilometers per second and measure distances in megaparsecs. But if you kind of think about this, this is distance over time, it's a speed, and this is a distance. So the dimensions of the two distance cancel out, and the Hubble constant has units of 1 over time. So you could, if you were a physicist and starting to do astronomy from scratch now and wanted to develop the field, you probably wouldn't have used megaparsecs as units, but that's what the convention is. And So that's what we use now and we'll keep using. And so I should probably stop here. I don't know if I should stop sharing my screen or what I should do, Saurav.
Okay, let me just check. I can stop share from here.
Okay, you'll stop it. Okay.
Okay. Yeah, Bharat, thank you very much. That was a very nice and fascinating lecture, and I really like those. Particularly, I like those demonstrations. Thank you again
Thank
for that.
you.
So it's time for to take few questions because we are already running out of time. So so during the registration, we ask participant to post their questions. So from there, uh, so wait a minute. Okay, so someone asked about if the universe is expanding, then it's like a balloon. Then as the balloon can expand by occupying some volume outside of it. So in the case of universe, is it occupying some volume like the balloon? I mean, perhaps he wants to ask what's the outside of the universe. I mean, which outer space it will fill if it's expanding.
Okay. So if you want to think about a balloon, so the space we live in is three-dimensional. So we can suppress the space, one-dimensional space, and think about this in terms of 2 dimensions. And one possibility is that the space is a 2-dimensional surface like the surface of a balloon. So in that case, you have to think of yourself as an ant, and all you can do is walk on the surface of the balloon. There's nothing inside the balloon, there's nothing outside the balloon, and the balloon is not expanding into anything. It just gets bigger and bigger. Distances between different points on the surface of the balloon get bigger and bigger. And I have a demonstration like this with the big weather balloon. I think Saurav knows the link to that talk, or you can find it on YouTube. It's a
Yeah,
talk I give.
I can
Okay.
share those actually. I can send the
Okay.
register. I mean,
Yeah, I think it's actually on our YouTube channel now. So if you just search for me on YouTube, it's a talk I gave in late 2019 when they announced the Cosmology Nobel Prize. So I mean, there's a balloon demonstration in there with the big balloon, but basically there's nothing. You're not expanding into anything, and there's nothing outside the universe. I mean, you can ask similar sort of questions. What's north of the North Pole? What's south of the South Pole? There's nothing there. I mean, the universe is everything in most models of physics. I mean, some people are willing to consider the universe as being little bubbles in an even bigger thing they call the multiverse. But we don't have much information about that or any measurements that suggest that's the case. So maybe if you look at that video on YouTube and you have more questions, you can email me.
Okay. There are various other questions like the observational evidences of dark matter and dark energy. I mean, if you can just quickly pass some comments about those evidences.
Okay, so we can start with dark matter. So there's a lot of evidence for dark matter. It's very, very strong that there is dark matter. All of this comes from its gravitational effects. And we make the assumption of a couple of things. We assume, so if we're talking about dark matter on the scales of galaxies, there's 2 assumptions that goes into that. So one is that Newton's inverse square law of gravity is correct. And the other is that F equal to ma is correct. Okay, so the way we measure dark matter is the same way as we measure the mass of the moon or the mass of a satellite going around the Earth. And you've seen this in many different contexts. If you're talking about this in terms of the solar system, they're called Kepler's laws. And what you do is you measure the velocity And if you think of this in terms of a circle, a circular orbit, so we have F equal to ma, and for a circular orbit, A is V squared over R. So, and we know what F is, it's G M1, M2 over R squared. So if you're focusing on a satellite, that mass of the satellite will cancel on both sides of that equation because it shows up in M1, M2 on the left-hand side, and it shows up in the mass on the right-hand side. The only mass that's left is the mass of the Earth. And so if you measure the time it takes for a satellite to orbit the Earth and the distance from the Earth to the satellite, or the distance from the center of the Earth to the satellite, you can measure the mass of the Earth. And you can do this by looking at stars orbiting in the plane of a disk of our galaxy, and you can measure how much mass there is inside their orbit. And you can then go and count up how much mass you see in stars and in hot gas. And we understand the evolution of stars very accurately enough to predict the mass of a star from its spectrum. So you can add up all the shiny mass inside the orbit of those stars you're looking at orbiting around the center of the galaxy in the disk. And you see that there's got to be a much more mass out there than there is in the shiny stuff. So if you believe in Newton's inverse square law of gravity, and you believe in F equal to ma, there is dark matter. So people have tried to modify Newton's inverse square law of gravity, and they've not been able to fit any of these observations on these scales. People have tried to modify F equal to ma, and the most well-known modification is called MOND, M-O-N-D, modified Newtonian dynamics. And it turns out that with MOND, you can explain this behavior of these stars in orbit around the center of our galaxy, provided, so what they do is they basically say F equal to ma is not valid for very small accelerations, but it's only valid for the large accelerations for which we're more familiar with. And there's some transition from F equal to ma at large accelerations to a different law at smaller accelerations. So there's some critical transition acceleration, which we can call A sub c. And if you can choose A sub c for a Milky Way galaxy, you can explain the behavior of stars in orbit around the center of our galaxy. It turns out you can also explain the same phenomena in Andromeda. You can explain the same phenomena in all other spiral galaxies. But the problem is that you have to choose a different A critical for each of these galaxies. So that might be unappealing to some people, that something as fundamental as F equal to ma depends on where you live in the universe. So if you're willing to accept that F equal to ma is not a fundamental law, but it depends on where you live in the universe, then you can explain these things. But when you look at dark matter on the scales of clusters of galaxies, this MOND explanation does not hold, it breaks down. And so you have to introduce dark matter again. So maybe you can resolve this issue of dark matter on the scale of galaxies through MOND if you're willing to accept that F equal to ma is not a fundamental law of nature. But even then, you cannot get away from dark matter. So dark energy is more difficult. So dark matter, in some sense, started showing up in the 1930s. Through Zwicky's observations. And so it's been around in one way or another for 80 or 90 years. I mean, even though it only started getting very seriously studied in the 1970s, so it's been about half a century. So there's a lot of evidence. And dark energy, the first sort of convincing evidence for dark energy only started showing up in the late or mid-1980s. And it's much trickier because the evidence for dark energy only shows up on scales of hundreds of megaparsecs or larger. And it's not like dark matter, where you can see dark matter in our galaxy. You can see it in clusters of galaxies. You can see it on scales of tens of megaparsecs. But dark energy, you have to go to much larger scales. And it's much more tricky, and the observations are much more difficult. But it shows up consistently with roughly the same amount of energy density in microwave background observations, in observations of galaxy motions, in observations of what are called baryon acoustic oscillations, in observations of the expansion rate of the universe as you look at it at different redshifts as you go back in time. So there's consistent measurements of the dark energy density, but the evidence for dark energy is much less secure than the evidence for dark matter. So I think maybe I should stop there, and maybe there's other questions also.
Yeah, Bharat, that was fine. So yeah, actually someone asked about this alternative theory like this modified gravity. So you have already answered that. So I think it's just time for the very last questions I can take from the chat box. So someone asked about can the cosmological constant be negative, or are there any kind of observational evidences to rule that possibility out?
It's pretty strongly shown to be positive at the present time. So we can do, so the universe is probably about 13.75 billion years old. And we can measure the expansion rate now, and we can measure it back to when it was maybe 5, 6, 7, 8 billion years old. And all those observations are consistent with a positive cosmological constant, or a slowly decreasing cosmological constant, which is what you call dynamical dark energy. And it seems to be all be positive, but I mean, things could change in the future. And so it's a very, very small contribution to the energy budget now, but it seems to be significantly positive.
Okay. So I think with that we can end this session. Thank you once again, Bharat. So I would like to request our IQC coordinator ma'am to give the vote of thanks. Thank you so much, Bharat.
Thank you, Saurabh. Am I audible?
Yes.
Yes.
Ma'am.
Yeah. So a warm and blissful evening to you all. Honorable Speaker, respected Principal, worthy members of Surendranath College, DBT-Star family, all the dignitaries from other institutions, valued viewers from different disciplines, and my beloved students who have virtually gathered here today for this popular invited talk to celebrate Science Day on a very interesting popular topic, organized by Department of Physics, Surendranath College, under DBT-Star College scheme. It's my proud privilege to propose a vote of thanks for today's wonderful revelation, patient hearing, and all the hard work behind the scene that has made this program a reality. On behalf of 4 DBT-Star departments of Surendranath College, I extend a really hearty vote of thanks to our honorable and esteemed speaker today, Dr. Bharat Ratra, for his most informative and interesting deliberation. Dr. Ratra has explored his cosmological topic very nicely today and has illuminated our curious minds. We are immensely grateful to him for coming here today, sparing his most valuable time in spite of his busy schedule. Thank you so much, sir.
Thank you very much for the very kind works.
Thank you, sir. I am extremely grateful to DBT, Department of Biotechnology, Government of India, for the funding, our college authority for their constant support, and our principal for truly being an inspiration to all of us. I compliment all the devoted members of Department of Physics for their tireless effort in organizing this webinar. Sincere thanks are due to all the members of technical team too for their cooperation. I thank all my students for showing great interest in this program. Their spontaneous presence has no doubt made these webinars so meaningful. Last but not the least, valued viewers from different institutions. We owe you a lot. Without your active participation, this event could not have been successful. I do sincerely believe the information and knowledge acquired from this webinar will be useful enough for our students and faculty members alike in the long run. Thanking everyone once again, let me end here. Surely we all will meet again with similar programs in these platforms or physically in offline mode very soon. Till then, all stay safe, stay awesome. Thank you one and all. Thank you very much.
Thank you.
Thank you, sir.